So today we will be talking about our CS536 project on TCP congestion control algorithm. So today we have reproduced and experimented on PCC Vivace algorithm, which is an online learning congestion control algorithm. This is basically a novel rate control protocol which utilizes ideas on optimization in machine learning. So here, basically, this algorithm introduces a rate control scheme that calculates that uses the gradient ascent algorithm, and it calculates that gradient using like a certain condition. And they have also introduced like a new learning theory informed framework for utility derivation. So the source code was publicly available, and we experimented on a bunch of things and modified the code and created new experimental settings and ran the experiments on on different and ran the code on different experimental settings and different values. So I'll be giving like a description of how this code is to be tested. So for this, we have submitted like the codes that are like present in this folder. So this is basically done as a Linux kernel module. So there are two things: the kernel Vivace latency and Vivace loss. So they're both compiled in the same way. I'll be showing one of them, and the other can be done in the exact same way in the different folder. So let's now talk about the loss one. So in this folder, there's a C file here. In order to compile it, we just have to run the command called main. There are a few warnings here, just ignore that. And then okay, sorry, it was probably already compiled before. Let me remove and start from the scratch. Yeah, okay. So let's compile from the start. Okay, there we go. Then now we will be using this congestion control protocol. Then there are server and client test files provided in this source code. In order to test this code, you can just run this server and client into separate terminals. So you can specify like a number of different parameters. They're all given in the code. So let's just call the server. We can specify the buffer size. I'm specifying it to be, let's say, 50. I'm sorry. Okay, and now let's call the client. Okay, and whatever that was written from that kernel module, we can actually see that by running the script file. So basically what is written from that kernel module is a description of like the throughput and like the rate, etc. So we have taken like an average of the throughput of these transmissions. So we can like see that by running the script.sh. You just have to run the script.sh and you can see that average. Okay, so this value sort of gives us like an approximate average of the throughput of these transmissions that are going on, the last 99 of them. So if we run them on different settings, we might get different values of throughputs, and that's what we essentially did. For example, in like our code, we experimented with the gradient calculation, and we also experimented with a number of different a number of different cutoff values for rate change, and also utility change. So I can give you like an example of that. Let's say this is the code that we essentially wrote. In their case, when they were calculating the gradient change, they were specifying a certain threshold below which, if the rate changes, they're not going to update the gradient. And we felt that that could have been a problem in terms of gradient calculation because it skips certain cases. So to handle that, we considered even those cases where the rate change is very small. However, we kept a certain weight factor because the main concern here was that there will be very noisy gradients and the denominator will be very high. And for that, we used a scaling factor to reduce the impact of those noisy gradients. And then we experimented with different values of that weight factor. We also experimented with, let's say, the okay, so yeah, we also experimented with the the minimum bound, that the minimum rate change bound that must be there, like um, in order for any calculation that they have done in this essential PCC apply change bound method, they have all in the existing code base, they had kept like a very fixed hard coded threshold for the rate change, but we essentially felt that that could have been a problem as well. So we experimented with other values as well to check if any of those improve the throughput. And we also did like a number of such different experiments. We also checked the utility change as well. So those are all like tested here in this code. So yeah, so they also they set several hard-coded values in the original code. The original implementer set several hard-coded values in lots of cases, and they assumed that this is the optimum value in several cases. But we tried to like address this limitation and experiment with a bunch of different values to see which one gives us the optimum throughput in that case. So apart from running the code, another thing that is present here is the visualization and the data. We have like a number of CSV files that gives the output that is generated from these runs. And at the same time, a plot Python file is given. If you run this plot Python file, it will generate like, it will generate basically a number of images that gives you, and that gives us like a number of different images that gives us some data in terms of how the throughput looks in terms of the buffer size and so on. For example, if we open this throughput CSV, we'll be able to see that there's like a bunch of data where they've compared a number of different methods. These are like the buffer sizes, and these are the Vivace loss, latency, cubic, etc. All of their performances compared to each other, and they are comparing all of these by changing the buffer sizes. So we did a similar calculation, but we also compared them for our new experimentation, and we have shown those results in the project report. So so in the end, we felt that the experiments that we conducted were essentially necessary for comparing a lot of different experimental settings that were in there in the current project. And it was an interesting learning experience for us, and we thoroughly enjoyed the project. Thank you.